Good afternoon, this is Schweitzer, and we're going to run a little video here on how do you quantify the level of acidic and or basicness. We've seen from our previous videos that H plus ions and the hydroxide ions are really the only two ways in which you can produce H plus ion, acidic or bases, acids or bases. So when it comes down to it, simply is this: anything that's acidic, the concentration of your H plus ions or H3O plus ions is greater than your concentration of hydroxides. And if you're basic, that just means your concentration of hydroxides is bigger than the concentration of your H plus ions. And then these two are equal if you're close to neutral. So with that being said, there's this one little kind of concept on the underlying sort of idea is that when we take a simple water sample, any water sample, and pour it out of your tap, you don't even notice it, but the water inside here is doing what we call auto-ionizing. And again, this is a small detail that for many people you either don't get exposed to it or you brush it off as being just a detail that's not important. But so what happens here is that this thing's constantly breaking apart into hydroxide ions and H3O plus ions. So we might have a solution that looks like this, where we have some H plus ions, we have some hydroxides, but the solution still, because they're equal amounts, is neutral. And, an hour later, you could examine this and see, oh, they've moved around, or there's those H plus attack the hydroxide, and when more water is split apart, they aren't guaranteed to be the same ones. Again, the solution is still neutral. So what does that mean? What it means is that this solution is going back and forth, waters breaking apart to form hydroxides and H plus ions. We have these guys attacking each other, forming waters, and we get an equilibrium system where there's a forward and there is a reverse reaction. And we get a bit of a stalemate where there's only a certain amount of H pluses or hydroxides that stick around, like we have here. You might look at here and think nothing's changed, but still going back and forth, back and forth. So what we do here, we come to this idea of equilibrium. Whereas if we were to write out an equilibrium expression for this thing, it would look like this. You take your products, which is your concentration of your OHs times the concentration of your H plus ions, and that is going to equal what's called your Kw. Again, it's written right here. That means, based on our rules of equilibrium, that the concentration of hydroxides, yes, it can go up, and yes, this can go down, or your concentration of hydroxides can go down, this can go up, but it cannot exceed this. So it's a bit of a teeter-totter between the two. But again, together they need to follow this algorithm. So now we have this algorithm that will help us predict one versus the other one. If we know how many H pluses there are, then we should know how many hydroxides there are. So we're going to use this particular idea, which is Kw equals concentration of H pluses times the concentration of hydroxides. If I know one of them, I can know the other one. The Kw is 1.0 e to the negative 14th. Now this is at 25 degrees Celsius. Okay. All right, so every single solution has a concentration of H pluses. Every single solution has a concentration of hydroxides because each of them are always present. In acid solutions, as we mentioned earlier, it's just that this is going to be very high. In basic, this is very high. And in neutral, they're about the same. All right, so calculate the correlating H plus ion concentrations. Okay, now we're going to use this guy here. So I'm going to just do this one up top here. We have, if my H plus ion concentration is 1.08910, what's the correlating hydroxide concentration? Pretty easy. I'm just going to do my Kw divide out, okay, by the concentration of H plus ions, and that will give me my concentration of hydroxides. It's going to be 1.0 e to the negative 14th divided by 1.0 e to the negative 10th. And that is going to give me 1.0 e to the negative fourth moles per liter of hydroxide ions. You'll notice that at this point, my hydroxides are bigger than my H plus ions. So this solution happens to be basic. Let's do this one. Now this one here would be 1.0 e to the negative 14th divided by 1.0 e to the negative 7th, which equals 1.0 e to the negative 7th. And of course now this is equaling this. Therefore that one is neutral. A couple things you might know is that for a neutral solution, okay, you always have to have this. This is the only combination that gives you a neutral solution. All right, this guy here is going to be 1.0 e to the negative 14th divided by 1.0 e to the negative 4th. And this is going to give you 1.0 e to the negative 10th. You'll notice now my hydroxide ions are lower than my H plus ions are higher. This solution is acidic. Okay, so now we have an opportunity to use this formula right here, and we'll keep this in our toolbox to be able to determine an H plus concentration if we know the correlating hydroxide and vice versa. And Kw is also a pretty important tool. Here's an example of just some of the work we did, showing the answers. All right, now again, doing all the math is one thing, okay? Once you do the math is pretty simple. But there's a different underlying concept here that I really want to make sure you understand. It's one of those things that I go on a bit of a rant in class, that if you see a number, okay, anywhere in life, okay, if you see someone who's 100 years old, you're like, whoa, that person's old. You know, that person's really getting there pretty old. If you see someone that way, has a size shoe like myself, that's like 10.5 is me, you just think that's pretty normal. But if you see someone who's got, like a friend of mine in high school had 18 size shoe, like, wow, wow, that thing is huge. That's a really big shoe. Or you could say a person that weighs, 160 pounds, that's fairly normal. But if that person is 2 years old, you're like, whoa, that's a really big 2-year-old. So every single number all the time that you ever use a number is automatically put on some sort of a scale, some sort of a reason to give it meaning. And for our purposes, that number is 1.0 e to the negative 7th. That's the neutral point. So if it goes up this way, H pluses go up, well, then this has to go down. If this goes up, then this has to go down, so on and so forth. Okay. So in this case, I should glance at 3 different examples, and I just want to know, are they acidic, are they basic, or are they basically neutral? This number is bigger than this one, so that means this went up, and therefore this thing is acidic. And I would expect my hydroxide ions to have gone down from this midpoint. This guy here is, again, now the hydroxides went up, so that means this thing is acidic. It means it's basic. These are high concentration, and these guys went down. And here, okay, so 1.5 negative 10th, okay, so that means the hydroxides are now below that point, so H pluses went up. This is acidic. So understanding this idea of just teeter-tottering on this thing is pretty important. So we have an acidic solution here that went up, therefore that this went down, it should be 1.0 e to the negative 10th. All right, so pretty important idea there. All right, so now again, we're trying to quantify this idea of acidicness. So we have this thing called a pH scale. So people are pretty familiar with the pH scale. This is going to be, let's say, 0 to 7 to 14. This tracks the H plus ion concentration. This is just an algorithm, a mathematical procedure that people created to help them deal with H plus ions. Again, keep in mind, as probably the turn coming into the 1900s, people were canning and processing foods for sale, and they got to use acids as preservation abilities. So they were finding all sorts of ways to use math to help make things work faster and, have less mistakes, less issues. Because if you could use math, then you could be more systematic and not have as much maybe problems with canning and different things. So in this situation, this tracks the hydroxide ion concentrations. Keep in mind, this is just a teeter-totter, and pretty sure that anybody here who's listening to this, if he gave you a few bucks to come up with an algorithm, you could calculate for a specific teeter-totter that's in a park, that create a mathematical algorithm saying if you knew the location of one side, you could figure out the location of the other side. So all you gotta do is track the H plus side to know where the other side is. You don't need to track both sides. For a given teeter-totter, you just gotta track one side and that's it. Same thing goes with the H plus ions. If I want to know how acidic or basic a solution is, I don't have to track both of these guys, just one of them. This is the one that kind of caught on, okay? Probably because of its use in food preservation initially. Okay, so here we go. This guy actually has a mirror image. It's 14 is the acidic range, 7 is neutral, and the basic range is 0. So right off the bat here, let's grab a little formula here for this guy, and it's going to be the pH plus the pOH equals 14. Okay, that's one that we'll see quite often here. Now, the pH system is based on an algorithm of exponential relation, so it's not linear. So in this case, the pH system, a pH of 0 is a 1 molar concentration. And 0 is going to be 14 on the pOH scale. This is 0.1, and this is going to be 13. This is going to be 0.01, 0.01, and this is going to be 12. 13 is 0.001. This is going to be 11. 0.0001. And this is going to be 10. Okay, so another way of saying this is 1.0 e to the negative fourth. 1.0 e to the negative third, 1.0 e to the negative second, and then 1.0 e to the negative first, and this is just 1, all right? Or 1.0 e to the 0. All right, so what would 7 be? 7 would be 0.000000, 1, 2, 3, 4, 5, 6, 7. Or 1.0 e to the negative 7th. The correlating concentrations, we've already done this formula right here, so you could take a moment and you could try out our previous formula, which is right here, and see if you can calculate the other side. Take a moment and we'll plug it in. The answers here is going to be 1.0 e to the negative 14th, 1.0 e to the negative 13th, 1.0 e to the negative 12th, and it just keeps going down. Negative 11th, 1.0 e to the negative 10th, 1.0 e to the negative 7th, and this would be a 7. So, and again, at this point we're neutral. And then the whole thing just flips it down, and this is the bottom here, it just reverses. So, last final question here, again, we're showing this for a reason. So you can see the relationship there, that you can estimate things. It's not linear though. So does a pH of 0.5 have a concentration of 0.5? And the answer is no. It's not linear. Okay, this is not the case. It's close, but it's not that big a difference between the two spots. So with that being said, what is it? Okay. On our next slide, we're going to show you how to calculate the actual value here. All right, so let's go ahead and let's go ahead and try that. Okay. Now on this one right here, okay, we have two different formulas, a couple formulas. One, this one we already wrote down. This one we already wrote down, and of course here's our little pOH scale. But what about this new one over here? To go from concentration of H plus ions to pH this way or back. Okay, we have this formula here and this formula here. Now this is where you're really starting to see this is an exponential scale. That is that log, and that means, well, it's an exponential relationship. We're going to go into it too much at this point, but you should be aware that's what it is. Okay. Now, how do we go about calculating these things? Well, first of all, also that this formula works for over here too. So, negative log of the concentration of hydroxides equals the POH. So you can move around. And every single solution has all four of these things, just so you know. And of course that formula works here too. Just swap out the name of the ion. Okay, so let's try this out here. So let's try it with our calculator. Determine the pH of a 0.5 molar concentration. So let's flip that around. Let's do the pH of, I think we did on this one earlier, we did here. The pH of 0.5 is what concentration? So let's go ahead and let's try that one here. I'm going to go, what is the concentration if I have a pH equaling 0.5? So let's try it out. So there's two different formulas here. The first one is using this guy. And that's what I want to use. Okay, so in this case, 10 to the negative 0.5 will give me my concentration. Okay, grab a calculator and you'll find that we're going to use a single button for this guy. We're either going to use the log button, okay, this guy, or we're going to use the second function of the log. You'll see that 10 to the x. So what we're going to do here is we're going to go, let's hit the second button, and then hit the log button, and up is going to pop a 10 to the caret, which you could just type in manually if you wanted to, and type in negative 0.5, and this is going to be the pH of what we were discussing. And what is the answer? Go ahead, take a moment, try it out. Negative, turn on the calculator, negative, okay, clear. So second log at negative 0.5 equals, and the answer is 0.3. Okay, so does that make sense in our scale here? Does it make sense that it's 0.3? Well, it's 0 is 1, 1 is 0.1, so 0.3 is between the two, which we would expect. And it's not exactly in the middle, which is also what we expect, because it's not linear. Okay, so in this case, I've now shown an example of that one. Let's try an example. Now this one here, I have what's the concentration? If the concentration is 0.5, okay, well let's just try that then. The other formula is negative log of the concentration. We just did pH 0.5, let's do concentration. 0.5 is this guy. What's the correlating pH? So we're just kind of reversing it, and let's see what happens. So negative log of 0.5 equals also 0.3. So this is one where it's fairly similar, so 0.301. And that'd be moles per liter. Let's try another one. Determine the concentration of HCl in a pH that is 2.5. So again, I want to go from here up to here. So I want to plug in this guy and get that one. Let's run it. So 10 to the negative 2.5 equals, but try now keep in mind, before we run this thing through, 10 to the negative second equals 0.01. Okay, so second, so that's the pH of 2 is 0.01. And then if you did negative 3, 10 to the negative 3, and this is, things that we kind of, you can estimate in your head, 0.1. So this guy's going to be somewhere in between here. Take a moment and actually calculate it out. So it's going to be second log negative 2.5 equals second log negative 2.5 equals 0.003. And of course, it's not right in the middle because it's not linear. And 0.003 moles per liter. So a couple different examples. Really, this is just a plug and chug problem, and you should be somewhat comfortable just trying them out. But again, you have to do them on your own, or it doesn't really matter. Every single solution, of course, has each one of these, and you should pause this. This is in general chemistry, honors chemistry. This is kind of our first kind of quiz on this topic. In a more advanced situation, we might just zip past it pretty quickly. So you still have to try a couple on your own. In this case, we're giving you this guy right here, which is 1.5 e to the negative fifth, and you should try a couple things on your own. Pause it, go ahead. All right, before we get start here, I'm going to go ahead and answer this question because I can. And I want to show you that, okay, this guy means that the hydroxides went up, so this guy went down, and my answer is should be basic. Now, people generally feel very comfortable using the pH to answer that question. So now on our little map here, we have H plus ions, we have hydroxide ions, we have concentration of H plus ions, and we have, let's just did that one. Let's do the, on the bottom, let's do the pH, and then we'll do the pOH. Okay, so in this case, the concentration of H plus ions, so we're located right here. It's like kind of on a map. You are here. Let's jump down here, and then let's zip over here and check out the pH. So we'll get that one and that one. So this is going to be negative log of the concentration of OH ions equals the pH. So it's going to be 10 to the negative, oh, no, I don't know why I said that, negative log of the concentration of 1.5 e to the negative fifth equals, okay, negative log 1.5 e to the negative fifth equals 4.8. Okay, so my pOH is 4.8. Of course, if you were to go on the scale of pH and pOH, you'd find that 4.8 is in fact basic. Alright, we'll now zip over here, which is 14 minus the 4.8 equals the pH. And we got 14 minus the 4.8 equals 9.2. Alright, so this equals 9.2, and 9.2 goes right here. Of course, that also correlates with basic. Now we have a chance to come up here or cut across here. Now both should get the same answer. And let's try this one once. 10 to the negative 9.2 equals, and then, so second log negative 9.2 equals 6.3 e to the negative 10th. Alright, 6.3 e to the negative 10th, and that's moles per liter. Alright, so that's our basic math of our pH system. And that is where we'll stop for today. And again, go to your workbook, try some problems out. Let me know if you have any questions.